Welcome to the third video on advanced algorithms. In this video we will again talk about dynamic programming, and we will look at the coin changing example, a different version of a dynamic programming algorithm for this problem. We will see how different way of thinking about the problem will lead to a different solution. So let's recall the problem. We have an amount of money we want to change. In this case it's 13. In the previous video we had 12. And we also have an array of coin denominations. We have a 10 krona coin, we have a 6 krona coin, and 1 krona coin. So in this case, to change with the smallest number of coins, you have to take 2/6 and 1 krona. One observation regarding the previous algorithm, the algorithm from the previous video, is that in principle it can output the coins chosen coins in any order. So it could say, to change 13, you have to take 6, then you have to take 1 krona, then you have to take 6 krona. Or it could say, you have to take a 6 krona, and then you have to take a 6 krona, and then you have to take a 1 krona. No matter which of the answers, both of them are correct, because each of those answers include the smallest amount of krona, of coins, in this case 3 coins. But the algorithm does not have any restriction in itself on the order in which the values of the chosen coins are printed, or for that matter chosen in the algorithm. So you can actually check, as an exercise, check which order will the previous algorithm output, the way we coded it in the previous video. But depending on how you program, it can output any of these orders, because in each step it considers which coin to take next, and this can be anything from all the available coins. One common idea when you thinking about dynamic programming solutions is to try to introduce some order. Sometimes it helps to make to design an algorithm. So in this case, let's try to think about looking at the coin denominations in the order of them in the array, in the denominations array, in the order of the decreasing value of these. So what we are shooting for is this answer, specifically this answer. Once we have an order in which we consider the denominations, then we can consider making a binary choice instead of a canary choice, as we did in the previous solution. There we said, okay, we can choose any coin here, so the choice in this case is 1 out of 3. We choose as the first coin any of these 3 coins. Now, if we say we start from the largest coin, and now the choice is binary, do we take it or not for this given amount? And then again, if we take it, then obviously we use it to decrease the amount, and we end up with a smaller subproblem, and then we again consider if we can take that coin or not. In some cases we will not be able to take that coin. This means that we have to go to the smaller coins in the array, and we will continue the process. So at this point you may want to stop the video, pause the video, and think about the recurrence resulting from this discussion, from this kind of binary choice. First we have to think which parameters define a subproblem now. So in addition to an amount of money we want to change, we probably want to have a parameter that says what is the largest coin we are looking at now and considering whether to choose it or not. So basically a position in the denominations array. So here's the recurrence for the version of the solution where you consider a binary choice. First, the subproblem is to find the minimum amount of coins when we have small a amount to change and I is the position in the denomination array that we consider. So then I is the largest coin that we can use, and then also we can use all the smaller coins. So we have a binary choice. Either we use that coin, then I, or not. Let's assume that we can use it. So the denomination of the largest coin that we can consider is smaller or equal than the amount we want to change, so we can use that coin. So the first option is to consider is to actually use that denomination. So we take the coin of that denomination, we count 1, and then we solve the problem where we have to change a minus then I amount, because we just used that coin. So we reduce the amount of money we need to change by the value of that coin, and we still want to be able to consider that coin one more time. Like in this case, we picked 6 2 times. So we do not move the index in the denomination array. We still have the same I. Another option is, of course, to say we will not use this denomination anymore. We move ahead in the denomination array. So we say we still have the same amount to change, but we move our pointer in the denomination array by 1. So these are the two choices that we can consider, and we take the minimum of the solutions produced by each of the choices. And of course, there is a trivial situation when we do not have a choice, when our denomination is larger than the amount we need to change. Then we can always use that, and then we solve a subproblem of having the same amount and moving one position ahead in the denomination array. So here we do not have the base cases of this recurrence. Try to think what are the base cases where we do not have to use the recursion. So here I added the base case, which is simple. If we arrive at the 1 krona denomination, which we always have in our array, then we know how to change any amount. There is no other option than just use a 1 krona coins to change the amount A. If A is 0, then obviously that is 0 number of coins. So that's the base case. Now we have to think about the table of solutions that we want to fill and how to fill it. So in the following we will develop a memoized version of this algorithm, but you can think how to write up the bottom-up solution. So to write an algorithm using this recurrence, we have to create an array of solutions to subproblems, which is a two-dimensional array in this case, because we have two parameters defining a subproblem, which is I, the index in the array, denomination array, and A, the amount that we are left, that we have to change. So we have this two-dimensional array that we will fill in with subproblem solutions. So we can immediately say that the space complexity of the algorithm is n times a. The memoized version of the algorithm is here to fill this array. First we fill the array with infinities, which symbolize unsolved problems, and then we call the main memoized function called coin change to m stands for memoized, with the parameters for I and a, 1 for I, meaning that we have all the array, all the denominations from 1 to n, and capital A, meaning that we want to change all the amount that we're given. The actual memoized procedure is here, and it just checks if the subproblem is already solved. If it is not equal to infinity, then I do not do anything, I just return it from the array. Otherwise, I solve it, just rewriting this recurrence into the pseudocode. So it's very straightforward. If I equals n, then I just return a, not return, but save in the first I save in the array and then return. Otherwise, I compute the two versions, the two solutions, with one without using this denomination I here, where I go to the next smaller denomination, or the other where I use the denomination, I call it use, which is again just a rewrite of this recurrence. So these are recursive calls. It's important to make the recursive calls and not just access the cells in the array, because we don't know if these cells are already computed or not. So we do a recursive call here. And then we see if the using the coin gives us a smaller amount of coins, we assign to C, I, or A, we assign use. And at the end we return this value. If we now want to augment the algorithm with the table of choices that we make, so that we can then reconstruct later, it's quite easy to do. We just have a table of choices, T of the same size, where we store true or false for each subproblem. True if this gives the smaller number of coins, so if I need to take the denomination, the coin of that denomination, and false if I do not take that coin. So what we can do is, we can program it in different ways, but what we can do is we can initially initialize the whole array T to be false. So T of I, A is false. And then whenever we see in the algorithm that we want to take a coin, we say that we take a coin. We say true. Here we need to take a coin. And also here we need to take a coin. That will give us a table of true and false values. What is the running time of this algorithm? As always when analyzing these memoized algorithms, we're thinking in terms of how many subproblems we solve and how much time we spent for each subproblem without counting the cost of solving sub-subproblems. So we can clearly see that there are n times a subproblems, and for each subproblem here we spent obviously a constant amount of work, so the running time of this algorithm is the same, n times a. Finally, to print the actual denominations that we suggest to use to achieve the optimal number of coins, we can easily use the t-table and write a print coins algorithm on that. Again, we just backtrace our choices starting from the original problem. So starting from amount A and I equals to 1, which means that we have all the denomination array from 1 to n, and then we just go, while there is some money in our amount, we say for this specific subproblem, if it says true, then we print that, we take that denomination coin, and we reduce our amount by that denomination to get a new subproblem. Otherwise, if it says that we don't have to take that denomination, we move ahead in the denomination array. You can try this out on the example from the beginning of the video and see how it works. To summarize, we have seen two different algorithms, two different dynamic programming algorithms following two different ideas. We have seen coin change 1, which uses a canary choice. At each situation it says I can choose any coin that is available to me as the next thing to do. And we've seen coin change 2, which uses a binary choice where we order our access to the denominations array, and then we consider if we take or do not take the largest available coin denomination. And we have seen that coin change 1 has running time which is n times a, and space which is proportional to a. So it had a subproblems, and on each subproblem it considered n choices in the worst case. On the other hand, coin change 2 again has the same time, running time, but uses more space. So here NA is because we have n times a subproblems, but we spend only constant time for each subproblem. We consider only binary choice.